Hi there. As you might remember, we have spoke about naive tokenization. However, we saw how naive tokenization has a lot of noise and special characters inside of the tokens, like dot, comma, and stuff like this. So today we are going to speak about algorithm that actually can figure out which of the characters are actually special characters in the text and which are not. And the algorithm are going to do this in absolutely language independent way. We also will show how the normal algorithms, how the classical algorithm with a language model may fail you because they almost always has predefined list of special characters, and this is not working well in real life, and especially in some cases when you, for instance, using a lot of emoji in your text and you're using emoji sentence separator and stuff like this. So yes, the only downside of today's talk, you need to be familiar with probability. So if you are not familiar with probability, please, before proceeding with the video, have a quick look on some of the link that I posted on the description to this video about probability from the awesome Stanford course, and then please come back and we'll continue speaking about our algorithm and how it actually can determine special characters out of the text without knowing any model about the text, and will work with any text. We'll have example with Russian, English, and so on. So but if you do know what is probability and how to calculate it, let's get started. So the one might think why we do need to find the special characters from the text. So why we can't just iterate through all the tokens, and we have this method is alphabetic character or is character that basically returns true for any character and false for not character, and then we can use stuff like this to basically figure out who are the special characters that's actually used during the sentence separation, and who are basically which of them are the part of the tokens. And this kind of work, but only kind of. So let me show you an example. This is like some of the text that was slightly modified, and it has a lot of emoji here. And one of the emoji, this one, this small guy that blinks you, he's basically used here as a dot. Let's try to put this text to an LTK. And this is actually a result of an LTK parser that tries to split the text on the sentence. And as you can see, this guy have no idea about the fact that this guy, this blinks you, he's basically a sentence separator. So as you can see, he finds only classical sentence separator. And in case of this is one side of the coin. So if you have a model that has predefined amount of separators, you are not going to find anything that is used as a sentence separator, but it's not canonical with the English language. And indeed, I have a lot of experience of parsing charts of young people who using emojis a lot, and a lot of classical algorithms like NLTK, they are usually fail to make a normal separation of the sentence. This is a good example. And at the same time, if you're going to try to figure out sentence splitter by just calling it character or not, you will receive false for all the emoji, not only for the guy who blinks. So you would try to split sentence, but by all the emoji, which again is not correct way. So as you can see, neither way are perfect, and we need something in the middle. And we're going to discuss exactly how we're going to split the sentence and find the special character that are splitting a sentence. So let's first import everything that we need. Let's define context with the text that we're going to use. As you can see, we will use Bible, we will use Alice in the Wonderland, and we will use the same emoji text, but slightly later. Let's start with Bible. So this is basically just reading emoji to the variable from the file. Let me create one more variable. Okay, so we are reading emoji. Okay, everything is fine. We're just reading 4 texts. Now let's do a naive tokenization as we have discussed earlier. and we tokenizing the Bible. Let's see some example of the tokens. So this is what we have done already before. This is just naive tokenization, and you can see some of the tokens indeed have this character that are not supposed to be part of the tokens. They're used as either sentence splitting or splitting the words inside the sentence, but they're not the part of the tokens, like comma, dot, and so on, so on. And by the way, see this semicolon that is not a sentence splitter or in the Bible almost all the time. Just keep this in mind. We'll discuss it later. So, okay, let's collect some data about the characters in this text. So what we need to collect for each character is how many times the character occurred in the text and how many times the specific character was in the end of the token. So this small simple snippet of the code does exactly this. For each token in the tokens and for each character in the token, we're going to have this special dictionary that stores count and end character. This is also counter that represents how many times he was occurred in the end of the token. Then for each character we're increasing his counter, and if this is an end token, we're increasing his end character counter. So let's see the example. Yeah, it will take some time. Done. Let's see example of the dot. So let's see data that we have for the dot. So the dot occurs in the Bible 26,420. At the same time, 26,2085 times it was in the end of the token. So almost all the time dot was in the end. After observing this data, you might start seeing that it's pretty easy to guess which character is actually a sentence splitter character, because he almost always in the end of the token. And hypothesis that you might have that let's calculate probability for each character that this character always in the end. So this probability is easy to be calculated. You just need to divide how many times character was in the end of the token onto how many times the character was in the text. So for dot, it's kind of almost 1. So it's really high probability. And you might start thinking that this metric is kind of a good metric to figure out whether character is special character that split the tokens or not. Because apparently in some cases it's not, because it hasn't been used in the end of the token, so it might be a part of the token. But anyway, so let's proceed with this hypothesis. Let's actually do the next stuff. This is just a cleaning. We are going to calculate the same probability for each token. So for each token in our dictionaries, for each key, which basically unique token, we're going to calculate probability. Probability that our token is basically end token. What is the probability that any particular token is the end token, and then we're going to save this probability. And just to see an example, let me show example for dot. Okay, so now for each character, an example is dot. We store how many times we observe this character in the text, how many times we observe this character in the end of the token, and probability that this token stays in this character in the end of the token. Now let's just basically sort by this field and let's see the result. So I'm just going to sort all the characters based on this probability and show you the result. Well, as you can see, results are pretty good. I can spot, like I'm showing first 20, but I can spot only one basically problem here. As you can see, my quote, which is here. And there is an explanation why it's here, because some of the quote actually in the beginning of the token, not in the end of the token. But majority of the separators are actually on top of the list, and even you can see this slight gap between probability of the last sentence splitter and the first non-sentence splitter. So it's kind of obvious where you need to put the line and say, okay, everything that is has bigger probability than blah, it actually token sentence splitter. Everyone that has probability less than blah, not token splitter. So it looks like hypothesis is working, and actually wrong. Let me show you more complex text. Let me show you Russian text. And as you remember, we're building absolutely language independent algorithm. Well, We still rely on some facts that the language is using spaces and stuff like this, but okay, less independent than many of the existing algorithms. So let's took Alice in Wonderland book, and this book is in Russian. So we're going to parse Russian text. Let me show you the example. So you don't need to know Russian, but you can see that we also have the special characters in this token that are not part of the token. So you don't need to know Russian, but you obviously can see that this is a comma and it's not a part of the token, or probably this. Okay, and let's apply the same hypothesis. So let's again, let me calculate data for each character. Let me show it to you. So for character dot, it was observed the text almost 2000, and it was in the end of the token slightly more than 1000. So let's actually see the probability. So the probability that dot in the end of the character in the end of the token is slightly less than 0.5. So it's like not a good metric, as you can see. It's not obvious that this is a separator token. Let's calculate again the same probability for all the tokens. And as you can see for dot, it's of course the same. And now let's sort all the characters by this probability. And as you can see, first character is this one, and then we have just characters. Then we have again something like this, and just character, and only then we have a dot. So we have a lot of mistakes, and these lists are not representative. You can't use this list because it's obviously wrong, something wrong entirely with these hypotheses. So how we can improve this, and how basically this works in AIF, and how AIF basically executes and finds pretty well all the sentence separators. So let me show you some improvements. Improvements are kind of hard, so I will slowly walk you step by step, explaining what is going on in the AIF brain, so you should be able to understand. But yes, please keep it focused, because yes, it requires some understanding. Okay, so first of all, let's ignore this part. This is just cleaning, just in case. We need all the tokens who are the size of which are more than 2. So all the tokens that include more than 2 characters. So if the token include less than 2 characters, we're just ignoring it. It's just that. Then we're taking from each token last character and character before last, and character before end. Then we reading character data. Character data is basically this dictionary that we have for each character. This dictionary. So we're reading his dictionary. Then we either reading dictionary from the field characters before, or if there is no such dictionary yet, we're creating a new one. And then for each character that observed before the end character, we increasing counter. Or if this is the first time when we observe such character, we're just setting it to 1 and then saving. So basically we are calculating all possible characters that observed before all possible end characters. So let me show the example of this dictionary for character dot. Okay, so what this basically means that, for instance, comma had been observed before dot 1 time in the text. Then dot was observed before dot 165 times. And then you see the normal characters, other characters of the language. And this character, which is a, like A in English, was observed 205 times, and this character was observed 108 times in the text before our dot in the same token. Why we need this, I will explain slightly later. Now we need to do some other work, some other optimization. We need to convert these absolute numbers to probabilities. So I need to understand if my token in the text ends with dot. Yes, so let's say I took random token from the text and this token ends with dot. What is the probability that character before is also dot or comma? So basically, in order to do this, it's kind of pretty simple. I'm just going to calculate sum of all these guys. So how many times? Basically, sum of all these guys should be equal to amount of the character dot, if we're speaking for dot, was observed in the end of the token. So I'm basically going to divide each of these numbers onto n character number, and this will be a probability. Let me show you the result. Let me show you the result for particular dot. Okay, so here is the result for the dot. What does it mean? So again, if I have a token from the word, and last character of this token is dot, then with probability, let's say 0.13, my previous character is also dot. Or with probability, who also have high probability here, or with probability 0.16, my previous character A. So by knowing that last character is dot, I see the probability of my previous character. This is very important metric. And last step that I will going to do. So let me actually put this one here, and let me show example with dot here. So what I'm going to do, I'm going to calculate in this part that if I take, let's say, dot, any character, dot has probability to be in the end of the token. This probability we have calculated earlier here. So we have probability that any character are end character. So if I take in dot, dot has probability 0.64 as an end character. Question: what is the probability that character before dot is actually end character as well? This is a pretty hard question, and I encourage you to actually go through this source code and to figure out how we're calculating it. And basically we'll see this power of 2. It will work without this power of 2. This is just some hyperparameter that was found on practice. But I encourage you again to go through this source code and slowly understand how we calculate this probability. But again, we need to figure out what is the probability that if you are the end character, you are in the end, like let's say dot, what the probability that character before you is actually an end character. And then based on this, you can figure out that you are a sentence splitter, because sentence splitter satisfies two criteria. First, sentence splitter had the high probability to be in the end of the token. This is first criteria. But as we saw with Bible, it's not enough. This criteria is not good enough in a lot of different cases. Sorry, as we saw with this book, because with Bible, it's actually good enough to work. Second criteria. Character that is observed before the sentence splitter also had to have a high probability of being in the end of the tokens. And this makes sense, because just think about it. So let's say we have a token end, and we have dot. D is usually characters that we can observe in the end of the token, but dot as well a character that we can observe in the end of the token. So as you can see, we have character that is easy to find in the end of the token, dot, and before him we have also character that are easy to find in the end of the token. So we have two consequent character, both of them are easy to find in the end of the token. So if any of the character has a high probability to be in the end of the token, and always when we observe this character, previous one has also high probability to be the end character, this probably means that our dot is sentence splitter. And let me show probability for the dot. It looks small. It really looks small. This our new fancy probability. It really looks small. But let's show me probability of other characters. And yes, it works perfectly. So if we're sorting by this new fancy probability, yes, it's small, and there is a way how to fix this, but this is out of scope. And you can see it works perfectly. we have these, we have everything except maybe this one, and only probably because it hasn't been observed in the text many times enough, because we have this quota that is actually recognized as a sentence splitter, and as you can see, it works perfectly well. And some of these formulas have like small problems. They are actually have small mistakes, but again, I encourage you to go through this small snippet to understand how it's calculated. And then this is version of the same algorithm. This is like the full algorithm in one place with small adjustment, and this is basically absolute algorithm that absolutely consistent with algorithm from AIF. It has like a slightly different tunings, small changes that was omitted in previous version that I just showed you, but anyhow you can look yourself, investigate, and see the difference. And I will of course post the link to this notebook for in the description of the video, so you can just download and investigate difference. And anyway, so let's come back to this example that an LTK failed to separate on the sentence with default English model. How we can separate this. So let's see how we will do with this text. So let's take the text, let's do an if splitting. Let me show you the characters. So actually, not going to show, we don't have as much characters here. Let me show you again, there is no dot here, so we have this failure. I'm not going to part this. Let me show you again, there is no dot here. We're calculating probability. Then let me show you this. Okay, so this is the character that have highest probability to be in the end of the token. As you can see, our smiling guy is not even the first one, but all of them have 0, 1 because all of them absorb in the end of the token. And this is completely insane. You can't work with this list, obviously. Now let's see our improvements, how it will work. Again, we have problem with this last line because we don't have a dot at all in this text, but don't be afraid. Let's just execute other part of logic, and let's show our end sorting. So this is the end result of our algorithm, and as you can see, it works perfectly well. Perfectly. It was able to figure out that sentence splitter is exclamation mark, comma, the smile, and question mark. And we don't have any language model. It's just pure magic that works. And it will work even better with our improvement algorithm from AIF. Again, I encourage you to investigate. However, we have the last problem. Last problem basically is the next one. How we're going to draw the line? So which probability is a special level of the probability? So if we're going to say, okay, everything that has probability more than blah is actually sentence splitter, less than blah is not a sentence splitter, or technical character, or sorry, not a sentence splitter, technical character. So everything that has probability more than blah should be separated from the token. How are we going to draw the line? How are we going to say that for this particular example, our probability is, let's say, 0.05. Everything that has probability more than 0.05 is actually a special character, and it should not be a part of the tokens. So tokens need to be cleared out of them. They need to be separated out of the tokens. And this is actually a separate question that we're going to discuss later. For today, we just figure out how to calculate probability that any character in any text are actually special character that is used for separation either sentences or inside of the sentences. And this is actually how AIF works. On the next lessons, we will show how to do it from Java, how basically the same logic works in AIF, and how you can improve or just basically dive to the same topic and see how it works there. And yes, and how you can improve it, and how you can use it in Java with your code with AIF. So thank you for listening to me. Stay tuned. Have a nice day. Bye.